Of course.
Why do we use the pH scale and not like the pOH?
So you do use both scales. Both scales are usually used. It's just because they're equivalent to each other, just opposite. The trend is that, usually you just use the pH scale because that's what people do in practice, right? That's why it's more common. It's the same way that all of physics would work exactly the same if we said down was the negative direction and up is the positive direction, or vice versa, right? All it does is change the negative sign and you just go with that convention. And the important thing when we're looking at that is just this relationship right here, right? Because if we have, man, it's doing this again now. Right there, that works. This relationship right here, if the H0 plus concentration goes up, to keep Kw the same, OH minus has to go down, right? Which means we have an acidic solution. Whether you're looking at pH or pOH, those things are equivalent to each other. If the OH minus concentration goes up, the H0 plus concentration has to go down, such that Kw stays the same. Why? Because equilibrium is where everything in nature moves towards, right? And for specific chemical reactions, this equilibrium constant is saying what are the concentrations of these at equilibrium. If I have a different concentration of these, then I have to adjust this ratio and the concentration such that they equal that number again, right? So these numbers can be different, but this always has to stay the same, right? If this number is different, then this has to change such that when you multiply them, they stay the same number. And that's a simplified version of equilibrium. All right, any questions on any of that? Okay, so why don't you guys take a second? We'll do one quick practice problem, and then we'll go into gases and hopefully finish gases before the quiz. If not, we'll finish gases in lab today. But if we have a solution has a concentration of hydronium of 2.7 times 10 to the minus 5, what is the pOH of this solution? All right, so C, using all the relationships that we've just defined or redefined or just restated, if you can figure out what the pOH of this solution should be. Let's go through and see if we can at least determine two paths, right? Two steps that we can do. And both ways we can do it will get us to the correct final answer. So does anyone have an idea? So we're starting from H3O plus concentration. What's the first thing that we can calculate to help us get the pOH? We can calculate the pH from this, right? We go to pH, and the relationship we use is the pH is equal to minus the logarithm of H3O plus, right? That's the relationship we would use to get to that point. And then from there, we can calculate what? What would be the final step here? We can get to the pOH, and what relationship would we use to do this? Yeah, we would use 14 equals pH plus the pOH. All right, so that's one way that we could approach this problem. Does anyone have another way? Or did anyone do it a different way? Yeah, we could use Kw, right? So if we start from H3O plus, we can use this Kw, right? Kw equals H3O plus times OH minus, right? And that would give us, what can we use that to solve for? OH minus, right? OH minus. And then once we have OH minus, we can then calculate the pOH how? All right, which of these relationships relates the P, Yeah, we just use our relationship. It would be this one here. The pOH is equal to minus the logarithm. So once you have this value, take minus the logarithm of that. That'll give you the pOH. All right, so we go pOH equals minus the logarithm of OH minus, right? And both of these should give you the exact same answer. All right, so let's say you have extra time on an exam. You can say, okay, well, I can go and calculate the pOH or the pH, either way, and it should give me the same answer. That's a good way to check your work. All right, so if you're to do method 1, pH equals minus the logarithm of 2.7 times 10 to the minus 5. Before we even plug this value in, should this value be equal to, greater than, or less than 7? What do you guys think? It should be less than 7, right? Because the exponent here, right, the way the logarithm works is it takes this exponent and it pulls it out in front, and then it modifies that number 5 right there. This 10 to the minus 5 is greater than, less than, or equal to 10 to the minus 7. What do you guys think? Which one's a bigger number, 10 to the minus 5 or 10 to the minus 7? 10 to the minus 5, right? That is a greater number, which means we have a larger concentration of H3O plus than 10 to the minus 7. So the concentration of OH minus has to be less than, greater than, or equal to 10 to the minus 7. What do you guys think? If H3O plus went up, what has to happen to OH minus? It goes down, right? It goes down to compensate so that they equal the same KW value. Right, so how would you classify this solution then before even plugging this in? Is it acidic or basic? It should be pH is less than 7, right? A low pH is acidic, right? So our scales, right, I'll do 2 different colors. The pH scale, this was acidic, this was basic. 7 is the neutral value, 14 and 1. And then the pOH scale, right, this was basic, 14 was acidic, and 7 is still the midpoint. All right, that's the pOH, and the pH scale is in red there. Right, so they just are opposite. They describe the same thing, just opposite, right? The pOH scale works in concentration of hydroxide. pH scale works in concentration of hydronium. But both of those work opposite to each other, which is why we can describe it either way. So we know this should be an acidic solution. And if you plug this in, you should get something like 4.57 for the pH value. So now you have a value for the pH, and now we plug it into our equation. 14 equals the pH plus the pOH. We rearrange this to solve for the pOH. So how do we solve for or isolate the pOH here? What do we do? Yep, we subtract, right, minus the pH from both sides. So this gives us 14 minus the pH is equal to the pOH. You plug in this value for the pH, and you should get a value that's like 9.43 for your pOH value. All right, so these problems are all going to be similar in terms of 2 different ways that you can solve for the pH, pOH concentration of OH minus or H3O plus, right? There's always going to be 2 different ways you can solve for it, and they're both equivalent to each other. All right, any questions on that before we move on to gases? All right, so that's a quick review problem for what would be on the quiz today. Right? And because these are dealing with concentrations, right, you can imagine these problems can be more layered in the sense that if I just give you the grams that you dissolved in a solution, what's the concentration of the acid, then what's the pH of that solution? If it goes through a chemical reaction, what are the moles of product if you know the balanced chemical reaction, right? So these things can all be layered into our comprehensive understanding of chemistry, right? Because concentrations, we've already talked about, we understand how those work. Now we're just describing it in the language of pH. And so if you look at the practice final, there's some examples of that using ideal gas laws, or gas laws and pH. But that's like more of a challenging problem. All right, how do you guys feel about that? Thumbs up, thumbs side, thumbs down? Thumbs up? Okay. All right, so let's go over gases. Let's power through gases. We'll go through the definitions, and then spend today in lab going over some problems for gases. And then also Monday, we'll go over just a review of gases and chemistry in general. All right. So gases, right, these are the least dense, right, the least dense and most mobile of the three phases of matter, right? Another way we could say this is that this has the highest energy of matter, right, because they have a large velocity, right? They have a lot of kinetic energy. And if we think about gases, it's easier to understand them in terms of their properties, right? So we can make what's an equation of state for them, which is the properties that are going to define the state of the gas completely, right? And we'll talk about what those are in a little bit. But these are spaced far apart from each other, right? So a lot of times what we assume in chemistry and in physics in general is that we assume most gases are ideal. And what this means is that we assume that they don't interact with other gas molecules, right? Because they're so far apart from one another, they're saying they don't feel the force of one another. Obviously, real gases don't behave this way, right? If they get close enough, they'll feel attraction for each other the same way other molecules and solutions and solids have intermolecular forces. Gases do too. But it's actually a pretty good approximation to assume that they don't interact with each other, right? They're generally so far apart from each other, they don't feel each other, right? So this means that they don't interact with other gas molecules. And so if you assume this, you can actually predict a lot of properties for real gases. However, one of the main things that you can't predict when you're looking at things like this is you can't predict a phase change for a real gas. If you compress an ideal gas, eventually you bring all the molecules right on top of each other. If they don't interact with each other at all, they can't form intermolecular forces to make solids or liquids. All right, so that's one of the limitations of assuming that you have a real gas. But in terms of most other properties, right? So if you ever taken a deflated, football or basketball or anything, you've gone up to the mountains. Does anyone know what happens? It inflates, right? It gets pumped with air, and it's not because you've added more gas to the ball or anything like that. It's because the external pressure, right, has gone down, and it's not fighting the internal pressure of the ball anymore as much, so the ball can expand, right, to its appropriate volume. And so you can use ideal gases to predict properties like that, right? The expansion of gas, equilibrium of pressures, and things like that. But we assume most gases are real. And I think a lot of the properties of gases, we have like an intuitive understanding of how they behave. And what are the properties that we understand gases with? We understand the pressure of gases. So the pressure, bless you, is the force per unit area of a gas. So even if you assume a gas is ideal, it doesn't interact with other gas molecules, you can say it still bounces off the walls of whatever container it is, right? When it bounces off the wall, it causes a change in momentum of the gas molecule, and it transfers a little bit of force to that wall. That force that it transfers is what we call pressure, right? Gas molecules bouncing on the walls of its container is the pressure it exerts on the walls of the container. And so this is denoted by the unit P, right? That's how we define pressure. And the units of pressure that we use are millimeters of mercury, atmospheres, and the bar. Right? So the bar, those are our different units of pressure that we use. Right? But fundamentally, what it is, in terms of fundamental units, is a force per unit area, which is a kilogram meters per second squared over meters squared, which would be our area. Right? So pressure is one of the variables we define the gas by. The other one we define it by is a volume. Right? What is the volume that the gas occupies? Right? So we think of a balloon. A balloon has a very specific volume. The temperature of the gas molecule we define as the letter T. This is measured in either degrees Celsius or Kelvin, usually. The volume, we use a liter, which is a meter cubed, or sometimes we use milliliters, and we know how to convert between those units. Right, the temperature of the gas, this is related to the kinetic energy, right? The kinetic energy, how fast are these gas molecules moving, right? As you heat up a gas, you expect the molecules to be moving faster, and then that is related to then the volume of the container, right, or the pressure, right? So for example, if you, you're boiling a pot of water and you put a lid on it, it has a tiny hole, what happens as the water starts to boil if the lid has a tiny hole in it? Or a teapot, what happens to a teapot once the water starts to boil? Right, it starts to whistle, right? Generally the teapot starts to whistle, and that's because the pressure inside is getting large because you're creating a lot of gas molecules. And that means that these molecules have a lot of kinetic energy, and they start rushing for the exit. They start exerting a large force, and they rush for the exit, and that pressure that goes through the little opening creates the whistling noise, right? So we intuitively have an understanding. If we increase the pressure, if we increase the temperature, we're increasing the pressure of the gas, and so on. And so we're going to kind of come up with what we would say an empirical relationship on how these things are related for gases. But there's an intuition. The empirical relationships follows our intuition for a lot of these. And the last thing that we can define a gas through is N, which is the number of moles of the gas, right? So all of these things are going to be directly proportional to the moles of gas, right? The more gas molecules you have, the more volume, the more pressure, and so on. Okay, so these are the things that define the properties that define a gas, right? So if we can come up with a relationship between all of these, we get what's called an equation of state between these properties. Right? So like I said, as we add more molecules to the system, right, the pressure of the system goes up, right? As you start to, if you think about this is just like inflating a balloon, right? If you inflate a balloon, except let's say instead of something that stretches like a balloon, you had a water bottle, right? Eventually, if you start blowing air into a water bottle, you can't blow any more air in because the inside pressure is larger than the pressure you can exert with your mouth and your diaphragm, right? You can't push any more air in there because the pressure is already so large it's fighting back against your mouth. That's directly what you're doing is you're adding gas molecules into the system, keeping the volume the same, and it's increasing the pressure, right? So as we add more moles, or the number of particles, gas particles, the pressure of our gas should go up, right? What else do we have? And we can derive a relationship. We can start deriving empirical relationships based off of these types of observations, right? So initially, these observations were determined empirically, and then later they came up with, theorists came up with equations that relate these exactly. And so we can also have a relationship between the pressure and the volume, right? So this is called Boyle's law. And it says the pressure of a gas times the volume, right? So the pressure is going to be a unit of force per unit area times the volume. This will ultimately say that energy is conserved before and after we've changed the volume of the system. And how do we interpret this intuitively? Well, if you were to take a balloon, right, and you try to compress it, what happens to the volume of the balloon, right? You're compressing it, meaning you're adding pressure to the balloon. What happens to it? Eventually it'll pop, right? So the internal pressure is going up. But what happens to the volume as you push on the balloon? What do you guys think? Let's say you could encompass it in your hand completely. As you squeezed it, what would happen to the size of the balloon, you think? It would shrink, right? As we increase the pressure, right, the outside pressure of the balloon, the volume goes down, right? The volume goes down. So intuitively, the way we think of this relationship, as we apply pressure to a gas, the volume goes down, right? And this means that pressure, right, if we increase the pressure and the volume goes down, how do we say those two are related? Directly, inversely, logarithmically, quadratically? How would you describe that? Inversely, right? As one goes up, the other goes down, right? So pressure and volume of a gas are inversely related. And the reason we want to build a little intuition for this is because when we're working on problems related to Boyle's law, it'll give us an idea of what should happen, right? So this is saying that this is our initial side, and our final side, right? Because these are inversely related, that if we start off at one pressure and one volume, then as we increase the pressure, the volume should change directly inversely, or not directly inversely, proportional in an inverse way to the amount of pressure that we're adding. Right, so how would we actually apply something like this, right? And if we build a little bit of intuition in regards to this, then that means that if we're given a problem and we know we start at a specific volume, a specific pressure, and we change the pressure of the system, we should have an idea, okay, my final volume should either be smaller or larger than what I started with. All right, so let's look at this example. If we have a sample of hydrogen gas, and it's at a volume of 5 liters and a pressure of 1 atmosphere, what is the new pressure if the volume is decreased to 2 liters at constant temperature? For these initial laws we're talking about, they're always going to have some of the variables held constant because they're not all changing at the same time. If you hold something constant, it allows you to ignore that when you're going through this calculation. So if the volume goes down, what do you expect the pressure should do in this equation? It should go up, right? Because they're inversely related. And how do we do that? Well, how do we calculate that explicitly? We use Boyle's law, P1 V1 equals P2 V2. Our initial pressure is 1 atmosphere. Our initial volume is 5.0 liters. And our final pressure is what we're going to be solving for, right? We don't know what that is. And our final volume is 2.0 liters. So we have to isolate P2 here. And how do we isolate P2? Yep, divide by 2 liters to both sides. What happens to units of liters on the left-hand side here? Cancels out. So what's the only unit that we should be left with on the left-hand side? Atmospheres, right? And that makes sense because we're solving for a pressure, right? Our unit should always work out. So we have to make sure we're keeping track of units here. 2 liters here, 2 liters there, cancels out. And I get that 5 divided by 2 is going to be 2.5 atmospheres is my final pressure when I plug this in. Does this make intuitive sense? Well, for the volume to get much smaller, that means I had to add a lot more external pressure to the system, right? So that means I had to almost double and a half or 150 times, 150% increase the pressure to get a volume change that we looked at, right? And that's because they're inversely related. So we try and build in a little of intuition and then use our intuition to understand our algebraic representation of this problem. All right. Any questions on that one for Boyle's law? All right. So the next law is called, and I'm not going to expect you guys to remember all of these laws. Really, it's just about using them, right? So another trick for these ones is if I'm given a pressure, a volume, and another pressure, and another volume at constant temperature, out of all the gas laws you're being given, you're saying, oh, I don't know which gas law to use. Well, the only variables I've been given in this problem are pressure and volume, right? Which means that I have to use this version of a gas law, right? So we'll see once we go over more of the gas laws why that's important. So the next law is called Charles' law, and this relates the temperature and the volume of a gas, right? So if you change the temperature, right, and it's expressed as V1 over T1, right? So that's the initial volume divided by the initial temperature is equal to the initial, or the final volume divided by the final temperature. And it's saying that if we increase the temperature, what do you expect to happen to the volume of the gas, right? If the gas is allowed to expand and contract, and you increase the temperature, what do you expect to happen? All right, what would you guys expect to happen intuitively? As we heat up the gas, what do you expect to happen if you heat up a gas? Let's say you had a flame-resistant balloon, right? But it could still stretch. And you start heating up that balloon, what do you expect to happen to the size of that balloon? It should get bigger, right? We can think about this, well, if I'm increasing the temperature of the gas molecules, that means they start moving faster, which means when they hit the side of the balloon, right? Ideal gases, they don't interact with each other, but they can still interact with the balloon, right? When they hit the side of the balloon, they're hitting it with a lot more speed, a lot more velocity, which is gonna push the balloon out, right? The balloon is gonna expand as we increase the temperature. So that means that as the temperature goes up, the volume also goes up. So how would you say those two are related? Yeah, those would be directly proportional to each other, right? If one goes up, the other goes up. The volume of the balloon increases. So the volume and temperature are directly related to each other. And they're directly proportional to each other. All right, if you take a balloon, I don't know if you guys have ever done this, but if you have a balloon that's inflated and then you put it in or so does anyone know, if you go to very cold temperatures, what happens to your tire pressure? It goes down, right? If you go to very cold places, your tire pressure goes down because your tire's trying to shrink because the gas molecules inside are colder. So that's why when you go up to the mountains, usually it's not a bad thing to have slightly more deflated tires on icy roads, but if you didn't want more deflated tires, you'd have to fill up your tires a little bit more as you go up to the mountains. Or you can overinflate your tires so they go to their normal pressure when you're in colder weather. Right? There's two different effects going on there, right? If you go to higher altitude, the pressure changes, but also it's the colder temperature that actually has a bigger effect. Okay, all right, so let's look at an example of this. So if you have a 2-liter sample of gas that's cooled from 298 Kelvin to 278 Kelvin at constant pressure, right? So we're keeping the pressure of the system the same. That's like, okay, we're just working at sea level at atmospheric pressure. What is the new volume of the gas, right? So we know that we're cooling the sample, right? If we're cooling it, what happens to the temperature? Does it go up or down? Goes down, right? And if the temperature goes down, what do you expect to happen to the volume if they're directly related to each other? It should also go down, right? They should both go down together. So we know intuitively, okay, that's what I should expect to happen. Let's see when we represent this algebraically if that's what happened, right? So our gas law is called Charles' law. It says the volume divided by the temperature initially is equal to the final volume divided by the final temperature. So our initial volume is 2.0 liters. Our 2.0 liters. Our initial temperature is 298 Kelvin, right? So we want to make sure that we're associating the appropriate values with each variable, right? Remember, with our, what were we working on? Oh yeah, M1V1 equals M2V2. The hard part of that is which volume goes with which concentration, right? It's the same idea here. Which volume goes with which temperature, which pressure goes with which volume when we're looking at our gas laws, right? So 2 liters is our initial volume, and it's saying it's cooled from 298 to 278, which means our initial temperature was the higher temperature, right? So that's why we put 2 liters with 298 Kelvin. And so that's equal to our final volume, right, of that we don't know, we're going to solve for, divided by our final temperature, which is the temperature we cooled to, 278 Kelvin. And so how do we isolate our final volume here? Multiply by what? 278 Kelvin on both sides. 278 Kelvin. What happens to 278 on the right side? Cancels out. And what about on the left-hand side? What happens to our units of Kelvin? They cancel out. So what unit are we left with? Liters, right? And does that make sense? It does, because we're trying to solve for a volume, right? So this is 278 over 298 times 2.0 liters. If I plug that in, 278 divided by 298 times 2, I get 1.8. These are all two sig figs, I'll just do 1.9 liters equals my final volume. And does this make intuitive sense? All right, does 1.9 liters make sense here? Why does it make sense? It's less than our initial volume, 2 liters, right? Which is what we expected. We expected as the temperature goes down, the volume should go down. That's our intuitive understanding of what's going on here. All right, any questions on this? How do you feel so far about gas laws? Thumbs up, thumbs aside, thumbs down. All right, so a lot of this is going to be identifying which variable goes to which variable. All right, and making sure our units work out, right? Because now we're adding, we've done a lot of moles, grams, molarity, liters. We're adding units of pressure and temperature into a lot of our calculations. So then we have the, not opposite, but the other thing we can hold constant is if we change or allow the volume to stay constant, we come up with what's called Guy-Lussac's law. And this says that as we increase the temperature, how do you expect the pressure of a system to change for a gas, right? If you were to, let's say, take a glass container that has air in it, right, and you put it over a Bunsen burner, what do you think will eventually happen to that glass container? It'll explode, right? Because the pressure inside becomes greater than the force that holds the glass together, and it explodes, right? So this is also saying that the pressure, right, so we increase the temperature, and the pressure also increases. So how are they related to each other? Right, if we increase the temperature, what happens to the temperature, or the pressure? It goes up as well, right? So they're directly related to each other as well. Pressure and temperature are directly related to each other. Right, and this also makes intuitive sense. It also means that if you took a balloon and you squeezed it, the temperature of that balloon also increases. It's less obvious because we don't necessarily feel when we're compressing things like that, but it also increases. As we increase the pressure from the outside, the temperature inside goes up as well. But that's why, example, the center of the Earth, besides radioactivity, is molten because pressures are so high there that it increases the temperature of all the liquid metal and rock that's at the center of the center of the Earth. Okay, so pressure and temperature are also related to each other. So if we have an aerosol spray that has a pressure of 4 atmospheres at 25 degrees Celsius, what pressure will the can have if it's placed in a fire that reaches 400 degrees Celsius? All right, so what do you guys think will happen? Do you think the pressure will go up or down? Up, right? Because if you put a can of hairspray or something in the fireplace, you're not supposed to do that. Eventually the can will blow up, right? So here we're taking something that's originally 25 degrees and it's then gonna be 400 degrees as our final temperature, right? So our equation for Guy-Lussac's law was P1 over T1 equals P2 over T2. Which pressure goes with what's P1 and what's T1 here? Yep, initially we're at a pressure of 4 atmospheres, and we're at a temperature of 25 degrees Celsius. And one thing I'll make a note of here is that in general, you don't always have to do this. So for example, if you're looking at a change in temperature, you usually don't have to convert to Kelvin. But when you're dealing with gas laws, in general, it's always a good idea to convert into units of Kelvin, right? So convert T to Kelvin, convert temperature to Kelvin, right? So the conversion, does anyone remember what the conversion is? Yeah, we'll just do 273.15 Kelvin, or 273.15 plus the degrees Celsius equals your temperature in Kelvin, right? So this is temperature in Kelvin of 25 degrees Celsius. And then your other final temperature is going to be temperature in Kelvin of 400 degrees Celsius. And we're going to solve for P2. All right, so make sure you do that conversion and then solve for the final pressure. All right, so I have to go pick up your guys' quizzes, so I'll let you guys work on this for a second, and you can take like a 5-minute break, and then we'll take the quiz when we're done with that. We'll finish the rest of gases, which isn't a whole lot once we are up in lab, right? So we're gonna use the rest of the time to take quiz number 4. All right, then this side? No problem. All right. Oh yeah, we'll go back to this one. All right, so I'll let you guys work on that for a while, then go use the bathroom if you need to, and I'll hand out quiz 4 when I come